Okay, rational functions and their graphs. Rational functions are quotients of polynomial functions. This means that rational functions can be expressed as f of x equals p of x over q of x. This just means one polynomial over another polynomial, okay? Where p and q are polynomial functions and q of x cannot equal 0 because we can never have a 0 in the denominator. We know that. The domain of a rational function is the set of all real numbers except the x value that makes the denominator 0, because that's when the whole world implodes. It is terrible. So we're going to find the domain of each of the rational functions. This is rational, which means a fraction. So we're going to set the denominator not equal to 0 and solve. Take x minus 3. You guys should be great at this by now. Not equal 0. We're going to add 3 to both sides. So x cannot equal 3. You assume all real numbers, right? So that means it could be any number on the number line from negative infinity to positive infinity except for 3. And it absolutely cannot be 3. So it could be any number here, but not 3. So our domain can be negative infinity to 3. We have to jump 3, pick back up on the other side of 3, and it can go to positive infinity. Okay? That's our domain. Now the next one. Once again, it's rational. Same thing, we're going to set the denominator not equal to 0 and solve. We have x squared minus 9 cannot equal 0. Let's add 9 to both sides. So x squared cannot equal 9. Take the square root of both sides. These cancel. X cannot equal plus or minus 3. Already assumed that it was all real numbers. So we're going to have a negative 3 and a positive 3. Now it could be any number here, any number in between the two, or any number after the 3. So here our domain would look like negative infinity to negative 3. Negative 3 to 3, and 3 to infinity, okay? Let's look at this last one. This is also a rational. Same thing, set the denominator not equal to 0 and solve. Okay, so we have x squared plus 9 cannot equal 0. Subtract our 9 from both sides, we have x squared cannot equal negative 9. Yep, you guessed it. Square root both sides. You guessed it, but you didn't see it, did you? Okay. Huh. So we can cancel both of these. So we have x. Oh, I forgot my plus minus. Oh, snap. Okay. X equals plus minus 3i. Right? Because you can't have a negative under an even root. Remember? So this automatically throws us into the imaginary. So that doesn't affect us, so our domain still equals negative infinity to positive infinity. Because it's not in our real realm, we're good. Okay. The real zeros of a denominator, g of x, although not in the domain, play an important role in the graph of a real function, and that is called your vertical asymptotes, okay? Definition of a vertical asymptote. The line x equals a is a vertical asymptote of the graph of a function f if f of x increases or decreases without bounds as x approaches a. So what this means is at x equals a, there's like this little imaginary line. As your graph approaches it, it'll shoot off to infinity, either one direction or the other. And that is your vertical asymptote, okay? Thus, as x approaches a from either the left or the right-hand side, f of x will go to positive infinity or negative infinity. So this is your f of x. And as it approaches your vertical asymptote, it will either go to negative infinity or positive infinity. Doing that every single time. It's pretty cool. Your graph will never cross your vertical asymptote. Okay? If the graph of a rational function has a vertical asymptote, they can be located using the following theorem. If f of x equals p of x over q of x is a rational function and is simplified, a is a real zero of q of x. The denominator then, the line of x equals a, is a vertical asymptote of the graph of f. So we always use our denominator to find our vertical asymptote. I'm going to underline that so you remember that. The denominator is used to find your vertical asymptote, okay? To determine the vertical asymptote of a simplified, I can't say that enough, rational function, set the denominator equal to 0 and solve. Like that. That's how you do it. But it has to be simplified. Since the vertical asymptote is a vertical line, it must be expressed in the equation of x equals a number. Once again, that's how it's got to be written. If you write it any other way, it's wrong. A rational function may have several vertical asymptotes. So you can have more than one vertical asymptote. Please remember that. Graph of a vertical function will never intersect. So that's what I just said a minute ago. It will never cross your vertical asymptote, okay? When graphing a rational function, a vertical asymptote is denoted by a dashed line. Never a solid line, always a dashed line. So these right here are I wrote these, just some things I find that are very, very important about asymptotes. So if I find them important, you probably should too. Okay, at least for the duration of this course. To find these, we set the denominator equal to 0 and solve. Let's do it. Find the vertical asymptote, if any, of the graph of each rational function. So we're going to take the denominator, we're going to set it equal to 0, and we're going to solve it, okay? So x squared minus 9 equals, oh, that's the wrong thing, equals 0. I just wrote it up on top. So sorry, guys. Okay, so we're going to add 9. X squared equals 9. Square root both sides. Don't forget your plus minus. X equals plus minus 3. Do not ever leave it like this. Remember, it's VA at x equals negative 3 and 3. Your homework is going to want it something like this, okay? Now let's graph it. Remember, it graphs as a dashed line. So we're going to go over here to negative 3. Negative 3. Now we're going to have to, on this one, we're going to talk about cancellations, okay? You always have to make sure it's in simplified form. Remember that. So here we have x plus 3 over x squared minus 9. You look at this and see that it's the difference of two squares, right? Because x squared minus 9 equals x plus 3, x minus 3. So let's write it like that. So what can cancel here? Absolutely, x plus 3. So that's going to leave us with 1 over x minus 3, okay? But when you have a cancellation like that, it does something really neat to a graph. So when you have a cancellation, there's always a hole. Hole created, okay? And to find where that hole is, we have to take the term that canceled. So we're going to take this x plus 3, set that equal to 0, and solve. So we'll subtract 3 on both sides. X equals negative 3. So there's a hole in the graph at x equals negative 3. So at negative 3, we're going to have a hole. So you denote that by a circle, okay? So denote hole. Then open circle. So wherever your open hole is, you make it, wherever your hole is, you make an open circle on your graph. That's called a discontinuity. Okay, so we took care of our hole. Now we're ready to get back to our asymptote. So let's jump back over here to our asymptote. We're going to set our denominator equal to 0. This is our, this is not our denominator, this is our asymptote, is what we want to say. So then we add 3 to both sides. So it'll be A. We're going to go over here to our 3. Don't never forget your restriction, okay, or like your discontinuity. Okay. And now let's work this one. So on the bottom here, let's factor this guy. Squared. Zero. Let's subtract our 9 over. This one just like before, or this is imaginary. Imaginary where there will be no VAs.